Alright, the purpose of this video is to give you some background notes on position time, velocity time, and acceleration time graphs. And we're going to be using the same keynote that's posted in Blackboard and to kind of talk through to fill out your note organizer. So when looking at position time graphs, first of all, just kind of identifying what they're showing you, we are graphing an object's location, its position in space, over time. And there's a couple things we can get off of that. The first major thing that we look for on a position time graph is a rate at which it changes its position. And that idea of how an object changes its position over time is what we call velocity. So as you're looking at a position time graph thinking how do you get the velocity from that, we have to take a look at the slope. So any 2 points that you want to compare and see how the position changes from, let's say, this point down here at time of 0 up to this point here at a time of 6 seconds, we could calculate that slope with the slope-intercept form, and that would be the average velocity across that time interval. One thing you'll notice that by looking at this first graph is that the slope is constant. And so our average velocity over the whole entire 12 seconds is in fact the same velocity at any given time period along that graph. Another major concept that we can get off of this is the idea of displacement. And for a position time graph, since displacement is defined as a change in position, all we have to look for is where the object started and where the object ends up for a certain time period that we're interested in. So what you can see on here is from 0 to 9 seconds, we started at 2 meters away, we ended at 12 meters away, and so the displacement that'd be calculated by just taking that final position minus the initial position, 12 minus 2, we've displaced ourselves 10 meters in 9 seconds. Now you don't always have to start with the very starting point, the 0 point down here. If they said what's the displacement from 3 seconds to 6 seconds, well then you would have this first point as your starting position, and then at 6 seconds use that as your final position. But the point is no matter what time interval they're looking for, you're strictly looking for how that position changed in that amount of time. Now this next graph off to the right shows a curved position time graph, and the concepts that we just discussed don't change just because it's a curved graph. The slope of the line is still velocity, and you still find displacement by taking final position minus initial position. The difference here is that your average velocity across this whole entire time interval is not the same as the velocity at any given time, or I guess it's not necessarily the same as any single time along the graph. In fact, you're only going this exact velocity at exactly the midpoint time. For this graph, from 0 to 7 seconds, it looked like we'd be going that same speed at around 3.5 seconds. So there's a couple different things that we have to make a distinction of when we have a curved graph. The first being the average velocity is still just the calculation from one point to another, finding the slope between those 2 points, and that tells you on average how fast you're going. We may be going slower before that, we may be going faster after that, but on average, that is the velocity that we're traveling. If you want to know the velocity at a particular instant in time, let's say at exactly 4 seconds, how fast is the object going? Well, that's what the second line here is showing, and technically what it is a slope line of a tangent to that curve. Now, it'd be really hard for us to draw tangents, but you have to find the slope of a tangent in order to find instantaneous velocity. We have a shortcut for that, though, as we mentioned. If I want to know how fast it was going at exactly 4 seconds, the instantaneous velocity, I could just take the slope from 3 to 5 seconds, because from 3 to 5, that average velocity across that time interval should be the same velocity that it is halfway between those two time periods. That's what we talk about when we say the midpoint time or finding the instantaneous velocity. Whatever time period we're looking for, we make it a midpoint time between two other times. Now, again, for this 4 second, I could use 3 and 5, I could use 2 and 6, I could use 1 and 7, as long as I make 4 halfway between the two. Now, with these ideas of position and time, we can write our math models, and we want you to fill those in down below. The math model for this graph up here is position equals velocity times time plus starting position, and the math model for a curved function is the quadratic function. This is actually in the form of a parabola, as we get a parabolic function from that graph. Now that you have the background info of what you can get off the position time graphs, I want you to pause the video and go down and answer the 4 questions below, referencing back to this material if you need to in order to answer those. All right, so the next graphs we're looking at are velocity time graphs. These are the most informative graphs that we come across in the motion unit. A velocity time graph can tell you quite a few things. We can start with what the slope tells us, and the slope of a velocity time graph is the concept of acceleration. It would be, in words, it'd be how it's changing its velocity per time. If an object is changing velocity, then it's accelerating. Well, as you see on this first graph, this velocity time graph, we have something going at 5 meters per second for 12 whole seconds, and that velocity never changes. And so if we were to find the slope of that line, that slope would still be its acceleration, except in this case we'd have 0 meters per second squared as our acceleration value. Over on this graph, ones that we're probably more used to seeing on a velocity time graph, we have something that is changing velocity over time. The velocity values are increasing over time, and this is showing an object speeding up as time goes on. Well, the slope of that line is again the concept of acceleration, and we could calculate that by just taking any 2 points and finding the slope of the line. Now, when we're looking at how the velocity changes from one point to the other, we would take a look, let's say at time 0 we had a velocity of 2 meters per second, and then at time 12 we had at 9 seconds we had a velocity of 12 meters per second. We would just be seeing how the velocity changed from 2 to 12 meters per second. So the difference there is that change in velocity, the delta V, from one point to the other. That's a rate at which it changed. That's how much it changed its velocity. The third concept that we can get, so we've talked about getting the slope as your acceleration. We talked about how you know what the change in velocity is. The third concept that we can get is what's called the displacement of the object, and we find that by taking the area under a VT graph. When we say area under a curve, we just mean we shade from the graph itself back to the x-axis. So you can see from 3 to 6 seconds we've shaded in that area. That is the concept of displacement. So what is displacement again from our previous slide? A position time graph, when you see position changing, that's its displacement, a change in position. So what this is doing is calculating for us the amount of position change, or the displacement. Over on this graph, we could do the same thing. We could see how the area under the graph shows you that value of displacement. The only addition onto this that I would make is you see how they shaded in this triangle. You'd want to shade this all the way back down to 0. So even these boxes in here you'd have to shade in, making this a trapezoid, or you can split up into a triangle and a square. I just noticed that that doesn't show up that way. So it's still area under the curve is displacement. When you're actually solving that, you want to shade all the way back down to 0 and calculate that full displacement for that object. For a math model, in this case our velocity is constant. In this case we'd have a changing velocity where velocity would equal acceleration times time plus initial velocity. Now again, pause the video and answer the 5 questions down below for this section. All right, last graph is an acceleration time graph, and when you're looking at an AT graph, we don't calculate slopes of these lines. There's no concept that gives us, so we don't go on and look at the slope of an acceleration time graph. Really all we get off of that is just values of acceleration, and we can also calculate the change in velocity. I'm going to show you how to do that. So the area under an AT graph will actually give you the concept of a change in velocity, something that we showed on the last graph as just going from one point in the graph to another. But the area under this acceleration time graph will calculate that change in velocity for you. Because it's acceleration versus time, that's what that area under the curve gives you. If you look at the slope of the line, that change in acceleration, that concept we're not really going to talk about, but in this case, this change in acceleration is 0. We don't change acceleration in this unit. We have constant uniform accelerations. So with that in mind, we would like you to answer those last 3 questions, and that is the end of this note session.